Balancing oxidation-reduction reactions is going to be the topic of this lesson. And we're going to find out that balancing redox reactions is a pain in the butt. It's not as simple as the balancing reactions you might have learned towards the beginning of this school year. So we're going to find out that, it's not just enough that you balance the elements, you got to balance the electrons. With electrons being transferred, that is actually easier said than done. But there is a process for this, and you just need to learn that process and work a number of examples to get it down. We call it the half reaction method. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so we are going to actually learn the half reaction method by doing. So I find it's often the best way to learn. And we're going to work two examples, and we're going to work an easier one, and then we're going to straight ramp it up to a harder one. But the easier one we're going to learn how to use the half reaction method is this one right here. And so you might look at this and be like, Chad, that looks balanced. One silver, one aluminum, one aluminum. And it looks balanced and the elements are balanced, but the electrons are not. And the evidence that you can see that the electrons are not balanced is that the charges are not balanced. So if you look here, silver's got a +1 oxidation state, and aluminum is in the 0 oxidation state. So we've got a total of +1 charge on the reactant side. But on the product side, so silver is in the 0 oxidation state here, but aluminum's +3. And so the total is the +3 charge on the product side. So we go from +1 to +3, and that means the electrons are not balanced. We've actually lost 2 electrons in the process. And again, in a properly balanced redox reaction, not only are the elements balanced, but the electrons are balanced as well. You can't just, gain or destroy electrons willy-nilly as needed. They go somewhere. So they're gained somewhere, they're lost somewhere, somebody's oxidized, somebody's reduced. Same kind of thing here. So this is not completely balanced, and what we do in the half reaction method is we split the overall reaction into 2 half reactions. One's going to be an oxidation half, one's going to be a reduction half. And so in this case, I don't really got much for options of what those halves might be. And so we're going to put Ag plus on one of them with Ag on the other side, and then we'll put the aluminums in the other one. So, and these are what we call our half reactions. And so if you look at this, when you've got a half reaction like this, you want to balance all the elements in your half reaction, but you want to save oxygen and then hydrogen for the last 2 elements you balanced, because there's special ways to balance those. Well, what's nice is that, one, the elements are balanced, and there's no oxygen, no hydrogen in either one of these, which is why this is going to turn out to be an easier example. So in the next example, we'll see what do you do when you do have oxygen and hydrogen, and it's going to be a little bit of a pain in the butt. All right, so the elements are all balanced, and there are no oxygens and hydrogens, and so life is good. And so the last thing you do is you have to balance the electrons. And you can balance the electrons by balancing out the charge. And so if we look here, so on one silver ion, we have a total charge of +1. And with just neutral elemental silver over here, it's 0. And whichever side has the overall higher charge, that's the side you're going to add electrons to. And in this case, you just have to add as many electrons to the more positive side till both sides have the same overall charge. And so in this case, we're going to need to add an electron, a single electron, to the left-hand side, because now with that negative charge and that positive charge, now the total charge would be 0, and they're both going to be 0. Now, one thing to note, in this case, they both turn out to be 0, and it'll be true in the next example of a half reaction as well. But the goal is not to make them both 0, just both equal in charge. That would be evidence that they have an equal number of electrons. All right, so in this one here, second one, we've got total charge of 0 for elemental aluminum on the reactant side, but a total charge of +3 on the product side. And so the more positive side is over here now, and we need to add not just 1 electron, but we need to add 3 electrons to make the charges balanced now. And so now we've got 3 plus and 3 minuses, and both sides are now balanced at 0. Now it turns out when electrons are a reactant, they're being gained, and so this is the reduction half reaction, we say. And so there's oxidation reduction, but we've now split those apart into separate halves of the reaction. And so this first one here, this is the reduction half reaction. So, and again, going from +1 to 0, yep, that's going down, that's reduction. All right, the next one though, when electrons are a product, they're being lost. So here aluminum has those electrons are his, and now he's been separated from those electrons, so he lost them. And so electrons on the product side is evidence they were lost, and this is the oxidation half reaction. All right, so now that you've got your half reactions balanced and the charge is the last part of them that you balance, then you've got to combine them back together making sure that the electrons gained in one of the half reactions are equal to the number of electrons lost in the other. And so in this case, this is a 1 electron reduction, this is a 3 electron oxidation, and you want the lowest common multiple between 1 and 3. So what number do both divide into evenly? The smallest number they both divide into evenly, in this case it's just 3. And so to make this a 3 electron process, it already is. But to make this whole half reaction a 3 electron process, what we're going to do is take the whole thing and multiply by 3. So, and then we're just going to combine the two together. And so notice it doesn't just triple the number of electrons, it triples the number of Ag pluses and Ags in the balanced half reaction as well. And so in this case, we'll combine all those together, and we're going to get 3 electrons here, plus 3 Ag plus, going to 3 Ag solid. Cool, so tripled the whole thing. And now because it's 3 electrons gained, and this one's 3 electrons lost, it is these that are now ready to be combined. And so we're just going to put all the reactants together on one side, all the products together on the other side, and make one giant reaction out of it now. So in this case, we'll still have our 3 electrons here, plus our 3 Ag pluses, plus now the aluminum, going to the aluminum 3 plus the 3 electrons there, plus the 3 silvers, and anything that shows up on both sides is going to cancel out. And so in this case, if you've done this properly, the electrons should always cancel out. 3 on both sides, that cancels. But now there's nothing that's exactly the same on both sides. And we'll find out in other examples that you commonly are going to show up with some things that'll cancel and stuff like that will show up on both sides. In terms of H plus and water, we'll learn later. So, but in this example, there's nothing. Ag plus doesn't cancel out plain old Ag. They have to be exactly the same chemical species to cancel. And so what we've got left is our balanced redox reaction. So this is going to come down to 3 Ag plus aluminum goes to Al3 plus 3 Ag solid. So, and one quick check, it's not a for sure guarantee that you're right, but you'll know if you're wrong right off the bat. It's just to check that your charges are now balanced. And if we look here, we've got 3 Ag pluses, that's a total of plus 3, whereas aluminum is 0, so it's a total of plus 3 on the reactant side. And then we've got the 1 aluminum 3 plus, which is plus 3, and then the silvers over here are neutral, and so it's a total of plus 3 on the product side, so both sides are plus 3. And again, that doesn't for sure guarantee that you're right, but if those charges didn't match, you could for sure know that you're wrong, and you have to go back and retry it. So, but this is our balanced oxidation-reduction reaction from the original that we started with. Now, what's nice in this reaction, there's no H plus in the reaction. And we'll find out, so in the next one, that commonly you're going to see H plus in there, and H plus is evidence that you have acid present. But it turns out redox reactions can be performed either under acidic conditions or basic conditions. And if you do have H plus in your final balanced reaction, so you'll find out there are actually 2 ways you could actually write it. One for when it's balanced in acid, one for when it's balanced in base. But if there's no H plus in your overall balanced reaction, then whether it's an acid or base, it wouldn't look any different, as is the case right here. But let's take a look at a harder example now. Okay, so for this next example, it's going to be a little more complicated here. We don't just have 2 elements. We now have 3 to worry about, and we'll see that it actually incorporate a 4th. So these redox reactions we're going to study are always going to be aqueous reactions. They're always going to be taking place in water, which means inherently you're always going to have H2O around, which often participates in these reactions, as we'll see. Now, one thing I want to do real quickly before we move on, though, is I want to talk about who's getting oxidized, who's getting reduced, who's the oxidizing agent, who's the reducing agent, and just kind of go through it in that context. So if we look here, the easier one to identify is the iodine reaction. So and we can see that iodine here is going from -1 to 0, and that's not going down, that's going up. And so here we could say that I minus is getting oxidized, which means that I minus is the reducing agent or reductant. Okay, so and that tells me going the other way here. So manganese is in the +2 oxidation state, and notice here manganese, don't look at that -1, that's for the entire chemical species. But if you actually just figure out manganese here, manganese is in the +7 oxidation state. We've got 4 oxygens that are going to be -2 each for a total of -8, and we add +7 to that to get the overall ion, polyatomic ion charge of -1. And so if manganese is going from +7 to +2, that's going down. It's a gain of 5 electrons. And so we'd say that manganese here is getting reduced. So, and is the oxidizing agent, sort of. And so in this case, if you say that manganese is getting reduced, not a problem. That's totally good. If you say that MnO4-, the permanganate ion, is getting reduced, no problem with that either. But if you talk about the oxidizing agent, you can't just say manganese is the oxidizing agent. You've got to give the entire chemical species is a part of as a reactant. And so in this case, you could say that MnO4- is the oxidizing agent, or the permanganate ion is the oxidizing agent, but you couldn't simply just say manganese is the oxidizing agent. It doesn't work that way. So I just want to make sure you saw an example that showed how when you identify the reagents, you have to give the entire chemical species as a reactant that it's a part of, not just the individual element that actually is changing oxidation state. So be careful with that. All right, so let's get to balancing this thing. All right, so our half reaction method, first thing we're going to do is split this into half reactions, and we can see that we're going to have MnO4- going to Mn2+, and while I'm in the half reactions, I'm just going to leave the phases of state off. They're just going to be tedious and get in our way, so we don't need them there, but I'll put them back in at the final end point here. So we also got I- going to I2, and there's our half reactions. So your half reactions are always going to contain what's changing, and here we saw that manganese is going from +7 to +2, so it's in one of them, and then iodine is going from -1 to 0, so it's in the other. So, but in this case, we didn't really have a lot of options anyways. But if you do have lots of options, you've got to figure out who's actually changing oxidation states, and then build your half reactions around that. Okay. So first step, split it up into half reactions, and the second step is to balance all the elements except for oxygen and hydrogen. Well, in the first one, the only element you have besides oxygen or hydrogen is manganese, and it's already balanced. There's one on each side. Okay, in the second one, you've got to balance the iodines first, and to do that, we've got to put a 2 right here. And now for both of our half reactions, all the elements are balanced besides oxygen and hydrogen. Then you go on to balance the oxygen second to last, and hydrogen's always last. And so to balance oxygens, these are aqueous reactions, you always add water, as it turns out. And so for the first one here, we've got 4 oxygens on the reactant side. We don't have any on the product side. To make sure we get some on the product side, we're going to have to add water. And in this case, because we need 4 oxygens, we're going to have to add 4 waters. The reason you save hydrogen for the very last, though, is that when you add waters, you end up adding a bunch of hydrogens to one side. And so if you did the hydrogens first, you'd have to readjust it afterward anyways. And so now we'll balance the hydrogens, and it turns out when you balance oxygens, you add water. When you balance hydrogens, you add H+. By default, we like to balance these in acid. Even though we might not actually be performing this reaction under acidic conditions, we can account for that later, but theoretically, we're always going to, by default, balance these under acidic conditions. And so it turns out we've got 8 H's on this side, none on this side. And so we're going to add H+ always to balance out our hydrogens, and in this case, we're going to need to add 8 of them. Okay, and in this one, there are no oxygens or hydrogens. All the elements are already balanced at this point. So now we've got all the elements balanced, and so now we're going to balance out those electrons. And so once again here, it might be easier to do the second one here, but we've got 2 of these iodides that are -1 each for a total of -2. And on this side, we're 0, so the elemental form. And again, whichever side is more positive is the one that's going to get the electrons. And you add enough electrons till both sides have the same charge. And so in this case, it's actually this side that's more positive, because being less negative is the same thing as being more positive. And so in this case, the number of electrons we need to add is 2, so that now both sides are -2. Okay, and so we see the second one here has the electrons on the product side, so these are being lost. This is your oxidation half reaction as we identified it earlier. So we said I- was the one getting oxidized. All right, now the next one here, kind of take a look at this, and students often screw this up just a little bit. We don't have to actually add up all the individual oxidation states, although that would work. It would just take a lot longer. We can actually just look at the overall charges of all the species combined. So here we've got 8 H+, that's 8 pluses. So, and then we got just a single permanganate here, which overall is -1. And so 8 pluses plus 1 minus is a total of +7. And on this side, it's just +2 because the waters overall are neutral. It doesn't matter that there's 4 of them. 4 times 0 is still 0. And then we have 1 manganese ion, which is +2. And so the total charge, let's put that in the proper place here, is just +2. And so in this case, +7 on this side, +2 on this side. This is the more positive side. And the number of electrons we need to add is going to be 5, so that now both sides will have a total charge of +2. And so I just wanted to point out again that your goal is not necessarily to balance both sides to 0, it's just to make them have the same charge. And you'll accomplish that by adding electrons, the appropriate number, to whichever side is more positive. All right, so we've got a 5 electron reduction and a 2 electron oxidation. So now our charge and our electrons are balanced. And now we've got to combine these back together, but the electrons gained in one have to match the number of electrons lost in the other. And so we've got to find the least common multiple between 5 and 2. What's the lowest number that both of these whole numbers divide into evenly? And that's going to be 10. And so in this case, to make sure that these both end up being 10 electron processes, we'll multiply this one by 2, and we'll multiply this one times 5. And so let's write those over again. And so in this case, we're going to get 10 electrons plus 16 H plus 2 MnO4 minus. And again, multiplying every coefficient by 2. So 2 Mn2 plus 8 waters. Cool, and then for the other one, we're going to multiply this all by 5, so 5 times 2 is 10 I minus, going to 5 I2s, plus 10 electrons. Cool, and now they're both 10 electron processes. And now we're going to combine them together, and again, all the reactants are going to go on one side, all the products on the other side, and we kind of already anticipate that these 10 electrons are going to cancel out these 10, and so I'm not even going to take the time to write them. They're going to cancel. All right, so let's combine all the reactants on one side, and we're going to get 16H plus 2 MnO4 minus plus 10 I minus, going to, and now all the products, 2 Mn2 plus 8 H2O plus 5I2. And this has been balanced in acid. And again, your key that you've balanced it in acid is the presence of H plus there. And so if your question said, balance this lovely redox reaction in acid, then you'd be done. But if it said balance it under basic conditions, well, then you have an extra step left to go. And so it turns out if you're under basic conditions, well, you don't really have a lot of H plus under basic conditions. You have a lot of OH minus instead. And so it turns out any H plus that, possibly could be involved in reaction would all get neutralized by hydroxide in a basic solution. And that's exactly the approach we're going to take. So to balance this in base, if you were asked to do it that way instead, once you've by default balanced an acid, then you focus in on your H plus. And for every H plus, you need to add OH minus, because H plus and OH minus are going to combine to form water. And if you've got 16 H pluses, well, then you need 16 OH minuses, and you're going to create 16 waters. All right, and then we add the rest of the stuff still in. So 16 OH minuses, these combined to give us the 16 waters. So the problem, though, is that we had a balanced reaction just a second ago. So if we had 16 hydroxides over on the reactant side, it's not balanced anymore. And so if you had 16 hydroxides here, you also have to add them over here as well. Now on the reactant side, they combine with the H pluses to form water, but on the product side, they're just going to be there. And they're going to be part of the balanced reaction at the end here. So let's combine this all together now, and we've got our 16 waters plus 2 MnO4 minus plus 10 I minus 2 Mn2 plus 8 waters 5 I2. Let's make that a better looking 5. And then your 16 OH minuses. So water, H plus, OH minus, they're all so common that you need to check to see if they cancel, because water, again, we always balance oxygens with waters. So water is just so common that when you just formed a bunch of them, you got to check to see, did I have a bunch already? And in this case, you've got 8 waters on this side, 16 on this side. So these 8 are going to cancel out 8 on this side, leaving us with just 8 left. And then we'll rewrite this one more time. 8H2O plus 2 MnO4 minus plus 10 I minus, going to 2 Mn2 plus. These are gone. So 5 I2 plus 16 OH minus, And this is the balanced reaction in base. Cool. Now, one thing we can do the same check both under acidic and basic conditions that we did a little bit ago, where we just make sure that the charges are balanced on both sides. And again, if they are, it's not a guarantee that you're right, but if they're not, it is a guarantee that you're wrong. And so in this first one, we got 16 pluses, 2 minuses. So we're at 16 pluses with 2 minuses, that's plus 14. And then 10 more minuses, that's going to be a total of plus 4 on the reactant side. And on this side, these are both neutral, so we don't have to include them all, but we have 2 plus 2s, that's also plus 4. And it's plus 4 on both sides. Works the same way in base. So here the waters are neutral, but we got 2 permanganates, that's 2 negative ones, and another 10 negative ones for a total of minus 12. And then we've got 2 plus 2s right here, that's plus 4. And then 16 minus 1s right here for another minus 16, which gets us also to minus 12. And both sides are minus 12. And again, so since the charges match, again, it's a good indication that we're probably right. It's not a guarantee. But again, had they not matched, you'd know for sure that you were wrong. Cool. This is balancing redox reactions. This process is just something you need to get down pat. And it usually takes students, a half dozen examples working through. So having the steps handy before they really get them committed to memory. So highly recommend you get some practice. Now, if you found this lesson helpful, would you consider giving me a like and a share? Pretty much the best thing you can do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on balancing redox reactions, check out my premium course on chadsprep.com.